Okay, so this is a free response question from 2010, and it's number 5. It's got a nice mix of A, B, and BC material in it. So looking at what they've given us a differential equation, dy over dx is 1 minus y. And then they're telling us that f of x is a particular solution, and we've got an initial condition of f of 1 is 0. And then it's saying for this particular solution, the y values, f of x, are less than 1 for all values of x. Sometimes they tie that into a slope field. In this particular one, they're just stating it. And we'll use that a bit later into the problem, but that is an important piece of information. On part A, using Euler's method. So we're going to start at x equals 1, 2 step size of equal size to get to x equals 0. So what makes this one a little bit different is that we're actually working backwards. So we're moving to the left on the graph versus moving to the right, which is typically how we see Euler's presented. So on part A, I'll just do that over here. So part A, where we're starting is at 1, 0. Where we're trying to go to is 0, something. And we're trying to find that y value associated with it. We're just doing an estimate, and we're moving backwards. So we're moving to the left each step. So we're using this slope equation. So y prime or dy dx is 1 minus y. And let's see, that initial slope at this point, 1, 0, the initial slope would be whatever happens when you plug the y value in. So that would be a slope of 1. And so we're going to start at the x value. I'm sorry, we're going to plug in a y value of 0, so the slope's 1. So we're going to start at an x value of 1, and we're going to move backwards a half unit to a 0.5, and then we'll move back another half unit to get to the x value of 0, and then we want to see what happens to y. So we're going to start with 0, that's our initial y value, and then from there we're going to move to the left. And so to move to the left a half unit, I'm going to go minus 0.5. That's the movement of a half unit to the left of the slope, and we're going to use the slope of, what do we say, that was a 1 for starters. So we're going to start at 0, move backwards a half step or a step, but worth 0.5 because we're spanning a space of 1 and we're cutting it into 2 pieces and then times the slope of 1. So it'll be 0 minus 0.5, so it'll be a negative 0.5. Okay. And then that means the actual coordinate we're at is 0.5 as the x value because we move back 0.5, and then y value negative 0.5. And now we're going to move back one more half step, so we're going to take that negative 0.5 and we're going to go minus 0.5 times whatever the slope is at that spot. Well, the slope at that spot, a negative 0.5, would be 1.5 if we plug in negative 0.5 into the slope equation. So let's see, it'd be negative 0.5 minus a half of that. So negative 0.5 minus 0.75, and that would be negative 1.25. And so now my question mark, because I moved back the other half step, the other 0.5 would be negative 1.25 or negative 5/4. We could certainly write that as negative 5/4. Showing the Euler's method, so actually just showing your work for the 2 steps is worth a point. And then coming up with a solution for f of 0 or an approximation for f of 0 is worth a point. Okay, so in part B, we've got kind of an interesting setup for L'Hopital's rule, which maybe is evident right away, maybe not. So we've got limit of f of x going to 1, f of x over x cubed minus 1. If you take and put a 1 in there, f of 1, that's our starting condition, that's 0. And then 1 cubed minus 1 would be 0. So we have 0 over 0. So this is, not infinity, I'm just throwing out random things. 0 over 0 is an indeterminate form, and that leads us to L'Hopital's rule. And so what we're going to end up doing is taking the derivative of the top and the derivative of the bottom. So we'll apply L'Hopital's rule. So let's see, I'm going to say limit as x goes to 1, f prime of x, and then on the bottom I would have 3x squared. Well, let's see, f prime of x, if we can evaluate that at 1. So f prime of x at 1. So I need to take and plug a 1 for x into the derivative, and I can't. It's got no input for an x, but it does have an input for a y, and I know that at 1, my y value is 0, so that means I'm taking 0 and putting it in. So that means the f prime of 1, and I'll actually write that, and on the bottom I'll plug a 1 in for x. F prime of 1 is 0. is plugging in a 0 for y is 1. So that value is 1. And then 3 on the bottom gives me a value of 1/3, and so that's our value for our limit. So applying L'Hopital's rule, showing that you're taking a derivative of the top and the bottom is a point, and then plugging in and solving is a point. And so you get 2 points for each of those, and 2 points for the steps on the front, and or for part A and part B. So that gives us 4 points total, which means part C is going to be 5 points. So part C, we have a particular solution. Find a particular solution to this differential equation. Now in AB, the only thing you could do is separate. Here we've learned a couple more methods on differential equations, which actually is what makes this a little trickier. Because at the outset, when you look at this thing, it does not appear in a separable format, or not something we're used to as separating. But this actually is just an AB skill. We don't have a way to pull this expression apart the way it's currently seated, other than to separate. But you have to be a bit creative with how you look at that. Maybe it's not creative, but for me, it's seeing that 1 minus y as being over 1. So then, or I guess, I mean, I always think of this as cross multiplication. So if I cross multiply, I'm going to get this dx over here, and then I have to move the thing with the y over to the other side. So I'm going to divide both sides by 1 minus y. And of course that cancels here, and then I've got this expression of dy over 1 minus y equals dx. And there are a lot of ways to get from this initial problem down to here. And I'm not saying my cross multiplication way is the best algebraic, but it works, it's effective, and one way or the other you have to see that you're separating. And then what we're going to do is integrate. So once you've got your variables separated, which by the way gets you a point, you're going to integrate. So we're going to integrate those things. Well, the integral of dx is just x, and we have to remember our plus c. And then the integral on the other side, technically you've got a u substitution going here, so you're making u equal to the bottom. It's kind of one of those u substitutions we generally, and the AP generally doesn't write, but if you really want to do it, you can definitely do u equals 1 minus y, do a du is a negative dy, and then negative du is dy. And then what that means is you're going to be integrating negative 1 over u du, which is ln. But it just boils down to you need a negative sign. And we're doing ln, and then we need absolute value bars whenever we get ln. So we have negative ln 1 minus y equals x plus c. You get a point for doing the antiderivatives correct, and then you get a point for the plus c. So this step actually nets us 2 points, meaning we only have 2 more to go. The next point we're going to get is for solving for c. So that's that initial condition piece again coming in. So f of 1 is 0. So I've got 1 comma 0 I'm plugging in, and I'm going to try to get what c is, or I will get what c is. So 1 goes in, that goes in for x, and 0 goes in for y, so I have negative ln of 1. Ln of 1 is 0, so c ends up being a negative 1. And solving for c gets you a point. So now we're at the spot. I'm going to take and just use this space over here to the right. I've got negative ln 1 minus y equals, let's see, what would that be? X minus 1. And now I need to get y all by itself. So the very last point comes with isolating y. So let's see, I'm going to divide both sides by a negative 1. And a fancy way to do that is just flip the negative sign, or flip the expression around, because if you divide by a negative 1, the x becomes negative, the 1 becomes a positive, or you can just interchange their position, and that gets you the same value. And you can write that any way that you want. I'm now going to e both sides, or take e to the both sides, however you want to say that. And I'm going to get this expression. And now here you actually run into a problem. We can't just arbitrarily drop the absolute value bars off. And it's actually where this little, what seems like a throwaway statement comes in. So for this particular solution, the y values are all smaller than 1 for any value of x. So what that means, and the only place it's used, is right here. That means all y values are less than 1. It means this expression that's in the absolute value bars right here is always positive. And anytime you have something in absolute value bars that you know is positive, the absolute value bars have no impact on the statement. So you can drop the absolute value bars. And now at this stage, I'm going to subtract that 1 over to the other side. And I'm going to again divide by the negative, which I'm going to use that little trick again. And there is my expression. you certainly are welcome to make some adjustments on it, but we've gotten y all by itself, and that does get us our final point. So in looking back on this one, first piece in Euler's application, second piece kind of being able to see the L'Hopital and how you would apply it, and then third one, understanding that yeah, we've looked at a lot of or more differential equations, but excuse me, seeing that this is just a separable problem and that this actually is an AB application. So 9 points total on this one. And again, this one was from 2010 and it was number 5, so no calculator.